All right, so guys, today, like I said, we're going to be starting the semester one midterm review. So, the midterm exam, we're going to talk about the structure of that exam quite a bit throughout the week, or really it's today and tomorrow. But what we're preparing for is an 18-question exam on Tuesday. 15 questions, 1 through 15 are multiple choice, and then 16, 17, 18 are free response. They're kind of those bigger progression type problems. And again, I will tell you this, that one of the things, I know that I had mentioned earlier that, again, this being a district assessment, there are certain things that we cannot touch, cannot change. One of the things that I personally would change for this is we did a lot of graphing first quarter. There are actually no graphs for you to draw. There are some multiple choice questions that are about graphing or deal with graphing. You saw some of those and how the questions would have been built, I suppose, on the first 28 of your assignment last night. But you noticed that on the multiple choice section, you didn't have to sketch a graph. You didn't have to draw a log curve. You didn't have to start with the parent function and adjust or anything. But you may answer questions about transformations and things like that. So, are there graphing type questions? Yes, but there's nowhere for you to physically draw a graph. Like I said, in the next couple of years, that's probably not going to be the case on CSA 1, but you're not going to be taking pre-calc in the next couple of years. You're taking it right now. So, again, just some various things like that. The goal that I have is relatively simple. And I know that we've talked about this before. Again, we've taken 3 chapter tests now and quite a few quizzes along the way. But hopefully you can say that every quiz or test that you've walked into, you've known what to expect. You've known what was going to be on that test. It's not a secret. I'm not trying to surprise you with anything. Same goes for this midterm. I want you to come in to class on Tuesday next week, and you sit down and you already feel like, yeah, I know exactly what's going to be on this test. It's up to me to now perform. Okay? It's kind of like, you're acting in a play or something like that. You know your lines. You're not expected to ad-lib once you get up there. You know the lines, but you still have to get out there and do it right. Okay? Or you're on the football team. You know the plays. Can you go out and execute? That's really what we're trying to do. Again, I'm not going to try to hide stuff from you and spring it on you. So, oh, yeah, I bet you weren't expecting that one. Again, that's not how I want to operate as a teacher. Hopefully that isn't how any of us are operating as teachers. But, again, that's probably another discussion. So, like I was saying few minutes ago before we started this video, we have the distinct advantage with this being not only multiple choice tests, but also being a common assessment in the sense that I know exactly which problems students struggled with last year and the year before and the year before. And there has been some variation. Don't get me wrong, there's been some variation over the years, but for the most part, the problem that was difficult 7 years ago was the same problem that was difficult last year, for the most part. And it has nothing to do with this group of kids compared to this group of kids compared to this group of kids. That's not it. It's because the problem was hard. It was a more difficult question. So that's why, again, more people struggled there. So what we are doing is, and I'm sure that I have it written down, but I think that I put the cut at 80%. Any of the problems that we were less than 80% successful on last year, we're doing a review problem that's very similar to it. Does that make sense? Okay? So a lot of these are going to look familiar if you did your assignment last night, because, again, it's not the same question, but it's, oh, yeah, this is like, I struggled on number 3 on the yellow. This is like number 3 was on that type of thing. All right? So as we're going through this, again, just like anything else, make sure that you're asking questions, and like I said, we'll tackle these one at a time. All right, so you're going to hear me whine about a few things dealing with the CSA. This is the first one. May as well just get it out of the way early. This particular question, I don't like it. Just couldn't be more clear. Don't like it. I feel like it's a little confusing to students, and maybe I need to get with the times as a pre-calculus teacher and change how we talk about symmetry. Again, I'm not removing myself from the equation here at all. I understand that this could be complicated. Because of the way that I or Mr. Bennock or Ms. Bender, the way that we teach these things. But at this level, symmetry is a graphing thing. When we talk about symmetry and, oh, what is this? Is this symmetric to the x-axis, symmetric to the y-axis, all that stuff? every time we talked about symmetry, which number one wasn't that big of a concept first quarter, quite frankly, but every time we talked about it, it was in reference to this graph right here. Then all of a sudden on the midterm, we have a problem that has nothing to do with graphing and it has everything to do with knowing how to algebraically calculate symmetry. This is something that if you have the best of memories, you might remember that we did like one example like this, and I think there was one homework question like this, didn't show up on our test, and then yeah, there it is on the midterm. Because again, to me, this is not a pre-calculus question. The good news is it's easier than that. This is more of like an Algebra 1, Algebra 2 question, but again, every year we have students that get mixed up because, again, we see symmetry and we're thinking about, kind of long-term, what is the graph going to look like? Yeah. All right, so the way that we're going to approach this problem, again, it says that we want to test x minus y squared equals 9 for symmetry with respect to the x and y axis. So I've mentioned having the graph may be beneficial. So for starters, getting this out of the way, you are allowed to use a graphing calculator on the midterm. So if you do not have a graphing calculator, I have 20 of them that I can lend out. So again, anybody who wants access to a graphing calculator has access to a graphing calculator here, I think, I hope. Again, just because we have a graphic calculator doesn't mean we automatically know how to use it, though. And also, in this case, if you do know how to do a little bit of graphing with your calculator, the fact that we have x minus y squared equals 9, that's going to make this a little bit tricky because we have a y squared value. We've got again, if you're graphing, we have to get to a situation to where we have y equals something. So we would still have a lot of calculation by hand to do anyway. So again, I don't know if that's our answer here, necessarily. All right, so this first problem, like I said, we want to test for symmetry with respect to the x-axis, y-axis. So when we're testing for x-axis symmetry, okay, this is really playing off of the whole idea of even and odd and all of that stuff. So when we're testing for x-axis symmetry, what we're going to do is we're going to take our given x minus y squared equals 9, but we're going to adjust the y. When I say we're going to adjust the y, we're going to put in its opposite. So what's the opposite of y? Negative y. So now that we've put in a negative y in place of y, we're going to clean this up. We're going to evaluate. If we get the exact same thing back, then we're symmetric to the x-axis. Does that make sense? So let's go ahead and finish. Let's test this thing out. We've got x minus. What happens when I have negative y and I square it? What do I get there, please? Just y squared, and that equals 9. So this is what we end up with. How does that compare to my original? It's the exact same. Because it's the exact same, then yes, we have x-axis symmetry. That makes sense? And this is kind of like the whole even and odd thing, right? Kind of like this whole even and odd thing. Dave, question? Shouldn't you said x squared? Should the y squared go away? Here? Yeah. No, so what that means is we have negative y times negative y. So the negative times the negative does make this positive, but the y times the y is going to be y squared. Okay? So one of the spots where some people have created problems for themselves is that they look back at this and said, okay, minus and negative, and then they change the signs. That's breaking the order of operations, isn't it? We have to take care of the exponent before we take care of, because technically that'd be like multiplying negative 1 times the negative y. But negative y is being squared, so we have to take care of the exponent first. All right? Okay, so you guys are really smart. Show that we can figure this out. We just did the whole test of the x-axis. We come over here to test the y-axis. What do you think we're going to do this time? And I hear change x. Is that what I heard someone say? Yeah, good. That's exactly right. So we're going to look at the original, which is x minus y squared equals 9. But in changing the x, we're not going to put an x in place. We're going to put a negative x in place. So as we clean this up, as we evaluate, now we're going to end up with negative x minus y squared equals 9. How does this compare to my original, please? Is it the exact same? It's not the exact same. Sure, it's close, but, you know, certain parts of it are the same, but it's not the exact same. So we'd say no y-axis symmetry. Okay? How do we feel about that problem, guys? Good? Good. All right. So we'll talk a little bit more about that as we go. Let's go ahead and tackle number 2. Number 2, it says if the area of a rectangle with a perimeter of 24, I caught that typo earlier, and then I apparently didn't change it. It's perimeter, it's not going to be square feet, sorry. So the area of a rectangle with a perimeter of 24 feet is given by A equals x times 12 minus x, where x represents the width of the rectangle. We want to use a graphing utility to graph the equation for the area of the rectangle and find the value of x that gives the largest area. So I believe that that second sentence that tells you to use a graphing utility to do this problem is actually making this hard, okay? Because I understand that a lot of us are either sitting there thinking, well, I don't have a graphing calculator, or I don't know how to use a graphing calculator. I wouldn't recommend that you actually use a graphing calculator on this one at all. You could, don't get me wrong, you absolutely could use a graphing utility to pull this off, but I, in some ways, think that that's going to make it a little bit more complicated. Okay, we have other avenues in order to that we could take in order to get there. So what this is playing off of is the idea that if we change the perimeter of our rectangle, if we change the overall look of our rectangle, but the perimeter stays the same, the area doesn't necessarily stay the same. So I guess what I'm saying, and I wouldn't draw this out if I were you, we could have a rectangle that's 1 by 11. Does that have a perimeter of 24? Perimeter. 1 plus 11 is 12, plus 12, yeah. So this has perimeter of 24, but its area, 1 by 11, is just going to be 11 square units, 11 square feet, okay? Could we draw another where maybe we have 3 by 9, okay? 9 here, 3 there. Also has a perimeter of 24, but what's this area going to be? 27, okay? Much larger area, even though the perimeter is still the same. So, if we're looking at this, is this just like, again, in my mind I'm thinking, all right, so as this gets taller, the area must get bigger and bigger and bigger, right? That must be what we're doing, okay? Well, what if we had a really tall rectangle? Maybe this is 10 by 2. Okay, 10 by 2 still has a perimeter of 24, but now its area, it's actually dropped a little bit. So what we're saying is that there's a sweet spot. Does that make sense? Now, if we're trying to look at this, we're trying to figure out which of these x values is going to get us there. We can think about this graphically. Now, please note that I'm not saying that we have to actually graph it out, but if we think about this graphically, when we look at a equals x times 12 minus x, are we noticing that that's quadratic? Might not look like it's quadratic until we distribute the x through. So distribute the x through, we have 12x minus x squared. Again, especially if we change the order, negative x squared plus 12x. Now, if we're looking at this, I don't think any of us are going to doubt that that's quadratic. Okay? What do the graphs of quadratics look like? What's the shape? It's parabola. Good. Now, I'm noticing that negative sign that's out front. So what does that tell me about the parabola? It's opening downward. Thank you, Reagan, for the physical demonstration back there. Yes? Okay, now, I don't know with any certainty if that's the least bit accurate, but roughly sketched in, that's what it's going to look like. Okay? Meaning, if the width is 0, the area is 0, right? But as the width increases, the area is also increasing until we hit a certain point, and then as the width is getting bigger and bigger and bigger, then the area is actually getting smaller again. Because if our width went all the way to 24, then that would make the height 0. It's not actually even a rectangle, but its area would be 0. Okay? So what we're looking for is that sweet spot. Well, again, let's start talking about this in the mathematical reality that we've just created. That's a parabola. What's that blue dot actually called? It's not the sweet spot. What's that actually called? The vertex. So if we can find the vertex, we have it. The vertex, this is going to tell us our width